Monopoly is banned at my house. My wife refuses to let me play the game with her siblings, and for good reason. Every time we try to play Monopoly, we'll find ourselves halfway through a game, and then inevitably an argument will erupt over some differing interpretation of the rules. Could be this rule over free parking, about where you put all the expenses, whether they go back in the bank or on the free parking spot. Usually it's about whether a couple of players are colluding a little too much. For all the frustration and tensions that this can create though, it may actually reveal something about our human nature. Because it's hard to imagine a pair of robots sitting down playing a game of Monopoly and falling out over the rules. They probably just get on quite earnestly, playing the best they can within those rules. And that may seem like a strange thing for a mathematician to reflect on, because after all, maths on the surface is all about rules. Surely we should agree on them up front. And yet it turns out that some of the most interesting, some of the most useful mathematics arises when we just dare to imagine what happens when we just break free of those rules, when we just tinker with them slightly. So, if you want to create a mathematical system, the first thing you have to do is declare your rules up front. You need something to bootstrap your system. So you need to lay out some starting points, a bunch of self-evident truths. These are called axioms or postulates. And one of the first people to do this around 2,500 years ago in Greece was Euclid. He builds a system of geometry using just 5 postulates. Now these postulates are very straightforward and intuitive. The first one says if you have 2 points in space, you can find a unique line that goes through those points. That seems obvious. Another says that you can extend that line indefinitely in both directions. That also seems obvious. And from these 5 postulates, Euclid, over 13 volumes of his major work, The Elements, proves over 450 theorems. Starts off with very simple stuff like how to construct an equilateral triangle using just a ruler and a compass, and then goes on to more complicated theorems. But he's able to trace every one of them back to those 5 postulates. But Euclid did have a bit of trouble with the 5th postulate. It's called the parallel postulate, and as the name suggests, it postulates the existence of parallel lines. It says that if you have a straight line, and you take any point off that line, then you can find a unique parallel line to the original that goes through that point. Now, Euclid's issue was that he didn't want to rely on this as a postulate. He wanted to show that you can actually derive it logically, that you can prove it from the other 4. And that way, he'd only have to rely on 4 postulates rather than 5. But Euclid never quite managed to do that. And then many others came after Euclid. For centuries, they tried and failed to prove that the parallel postulate follows from the others. And the reason they failed is that it doesn't. However obvious and intuitive that 5th postulate seems, it simply doesn't follow logically from the others, which rather begs the question, what else is there? What happens when you violate that 5th postulate about parallel lines? What other geometries could that give rise to? And to get there, we're going to solve a riddle. You may have heard this before, has different variations. In this version, we have a mathematician, and a mathematician walks 1 mile south, then they walk 1 mile east, and then they walk 1 mile north, and they end up back to where they started. Now that already doesn't seem possible. And then the riddle goes on. They see a bear. What color is the bear? Now the bear may be the giveaway to this riddle. Any riddle involving bear usually leaves you at the North Pole because we're talking about polar bears, and that is the case here. The answer is white. But let's think about the mathematics of what's happening here. We're now on a curved surface. We're on the surface of the Earth. We may as well approximate it as a sphere. And we're at the North Pole. And if you think about the path that explorer takes, they start at the North Pole, they go south, then they walk across, they go east, and then they go back up. And there's something very interesting about that triangle. It has at least 2 right angles. If you think about the path they take 2 90-degree turns. It may even have 3 if that triangle's large enough. But it will definitely have 2. And among other things, that means that the angles in that triangle add up to more than 180 degrees. Now that doesn't sound right. At school we were taught that angles in a triangle add up to 180 degrees, and we never thought to dispute that. So what's happening here is that Euclid's 5th postulate has been violated, and we're in an entirely new geometrical realm. So it turns out that Euclid's geometry works perfectly well in the flat plane. You get your 5th postulate, you get your parallel lines, angles in a triangle add up to 180 degrees, no problem. But if you then change the surface, so now you have a curved surface, like the surface of the Earth, well now that 5th postulate doesn't hold anymore. We have a very different notion of what we mean by a line. In this new geometry, a line is any circle that wraps around the sphere and splits it into 2 equal parts. In other words, any type of equator. And the thing about all of those lines is they all intersect. So in this geometry, there are no parallel lines. The fifth postulate is no more. And one of the consequences is that angles in a triangle add up to more than 180 degrees. And there are other geometries as well. That's a spherical geometry. You can also define something called a hyperbolic geometry, which goes to another extreme. It says you can have multiple parallel lines. In fact, you can have infinitely many parallel lines, not just one. You get this on saddle-shaped surfaces where every point is curving outwards. And one of the consequences there is that angles in a triangle add up to less than 180 degrees. So we now have three very different geometries, three fundamentally different ways of thinking about shape and space, and they all arise from this tinkering with that very simple rule around parallel lines. Now, I think this signals something really very deep about our human creativity, because it's one thing to work within a set of rules, to combine them in creative ways, and that's something we are seeing computers do more and more of. But it seems to me that there's something distinctly human about this willingness of ours, this daring that we have to actually break out of those systems, to break free of those rules, and to dream up new worlds in the process. And it turns out that mathematics is an exemplar of this type of creative thinking, because so much of the mathematics that we take for granted today originates from that willingness of a few people to just depart with accepted convention and break the rules. So remember, in mathematics, rules are made only to be broken. If you're feeling slightly anxious or uncertain about artificial intelligence and what it means for us as humans, then go buy my book, Mathematical Intelligence. Over 7 chapters, I lay out 7 different ways of thinking mathematically that I believe will give humans an edge over computers.